8.4. It's all about trigonometric identities. And let's list some of the ones that we already have. We already have the Pythagorean identity, and that is that you have your cosine squared theta plus the sine squared theta is equal to 1. You also have another one such as the tangent of theta, and that's just the sine of theta over the cosine theta. These are some common ones that you already have at our disposal. We just introduced Euler's identity, which is not explicitly a trig identity, but it's related, so I'll put it here. It's Euler's identity, another important identity. And what we just discovered about the sine and cosine. And the sine over here as well. So all these different identities, you know, the Pythagorean and some other ones. Here's the Pythagorean, that's the ratio between the sine and the cosine, Euler's identity, Euler's relation for the cosine, Euler's relation for the sine. And now we're going to start to derive new identities. So the next one we just derived was the double angle identity. So now you introduce the double angle identity. There's two of them. There's actually identities. We started with the sine, and we'll look at the cosine momentarily. And we have now the sine of 2 theta is 2 times the sine of theta times the cosine of theta. And we were able to show that simply using my Euler relationship, and these three gave me that one. There's a whole series of additional identities from this as well. You also have one that we're going to show a little bit tomorrow. I'll put them in. Here's another double angle identity, and that's with the cosine. Now the cosine 2 theta, it's a little more complicated looking. It has several different varieties of it. There's one version. Cosine squared minus the sine squared. And then if we kind of use this around in different ways, we can get additional of these double angle of identity. So you can get cosine 2 theta, you know, or I can replace, if I wanted to, my cosine squared with, if I replace the cosine squared with 1 minus the sine squared, what do I get? I get 1 minus 2 sine squared theta. How do I do that? Well, cosine squared from this over here, solve that for the cosine squared. Cosine squared theta is 1 minus the sine squared. Well, put 1 minus the sine squared, I have 1 minus sine squared minus sine squared, minus 2 sine squared. And we'll show some of those and how to get them. You know, once we get this, the other ones just follow by using other identities. Or I could replace the sine squared with 1 minus the cosine squared. So I could also have the following additional trig identity. This is what's so, you know, confusing about the trigonometric functions. There's so many different relations between them. This would give me 2 cosine squared theta minus 1. So we're going to be looking at these double angle identities further tomorrow. We just did this first one today. And then we also have products and sums of angles. So that's going to be, in addition, tomorrow we have the, or something, not product and sums, but sums and differences of angles with our trig functions. So tomorrow we'll spend a little time, we'll look at the sum, we'll look at the sine of angle A plus B. And we're going to show that that is equal to sine A cosine B plus over here sine B cosine A. That's a sum. If I want to put in a difference, all I need to do is we'll show this. We haven't shown this, but we're in a minus over here. That's the sum and difference of two angles in an argument of the trig function. I can break it up so it's just the individual angles. It's not a sum. So I get rid of the sum and difference and put the sum and difference between the two. So that's another, if you will, version of trig identity. We have one for the sine, and we also have an additional one for the cosine. Very similar. Now we have cosine of A plus B is cosine A cosine B. Now the plus here leads to a minus over here. Sine A sine B. And if I take and subtract here, that turns into addition there. So these are some of the, much more popular ones that we see over here. And we also have one for the half angle identities and other things as well. And we're going to continue on. I'm going to show you additional ones. Now, typically, obviously, these are your most, I'll put it in red, the most important ones of the group over here. Now that you should know hands down. That you should know hands down. You should have a sense for this, and these two, you can work these out. But this is something that you should know. Those are very common. These other ones, you don't have to commit them to memory. You just have to know that they exist, and you can quickly look them up. I mean, if you remember them, because sometimes you mix up, is this plus, is this minus? I mean, you can work around that by putting known angles in there and get it to work out. And you can put 45 and 45 for here and determine whether it's a plus or minus. But you need to just know that they do exist because they will become useful at some point in your mathematical career. So you may not use them as much, like with the cosine, you may not know this as much. The sine 2 theta is a very, very common one. That's something that is extremely important. And then we're going to be looking at half angles, identities, and stuff like that. So after the sum and differences, we'll also look at half angle identities. So we have double angles, sum and difference angles, and half angles. Those are the three most common categories of trig identity. And what do? A lot of times in calculus, you have a lot of these trig functions. And what you need to do is you need to rewrite them in a form that you can do something else with them, such as we're going to call integration or things like that, or differentiation. So these trig identities help you to rewrite them. And what we're going to do after this, we're going to show how to work with these things and derive new identities from old identities. These are not the end of them. The list gets even longer after this. This can take up, several weeks worth of time if I wanted to spend the time on it. We don't have that much time. We spend a little more time on it when we do this in our, Quick Cal 1 and 2 because we have 8 credit hours to work it in. Here we're just doing it in 4 credit hours but 5 contact hours. So we have a lot more time to spend on it. It's not so critical in the calculus. If you understand the beginnings of this, that is much more critical. And just understanding that there are relationships that you might be able to use later on. So you don't have to commit all these to memories. On the test, I will allow a sheet that will have the identities. Now, some of these, when you use them on a regular basis, they'll be just like the quadratic formula. Most of you have probably committed that to memory, as well you should, because if you use it a lot. This identity, you should commit to memory. But the other ones, if you don't memorize them, it's not going to be critical. Okay, So we're going to do more on this tomorrow. I just wanted to kind of set the stage how this Euler identity here, it's an amazing, like I said, it's one of, people consider it the most beautiful theorem in all of mathematics. It's how it connects all these different branches of mathematics in a simple, very simple way. And it's very elegant. And then it goes from there. And this kind of derives of all these other things. And it kind of gives a meaning. What does it mean to raise something to a complex power, like an imaginary power? We know when it's, 2 squared or 2 cubed, that's 2 or 3 factors of 2 multiplied. But e to the I theta factors of e, well, we've shown that that is really equivalent to multiplying complex numbers. And that's an interesting thing. That's why we introduced the complex number, because they're so fundamental in how all this stuff is connected together and eventually ties it all together to let us study the calculus. Okay, the homework for this is relatively simple. I just mainly did all the work for you here. 8.4, which is all about the trig identities. And I'm going to list them over here, just because these are the things that you should be familiar with. On a test, I won't require you to memorize them. You'll be able to look them up, but you need to know how to work with them, and we'll talk about that more today. So what we have is we have our, double angle. Well, we have the Pythagorean theorem. So one of the first ones that you need is cosine squared theta plus sine squared theta is equal to 1. That's our Pythagorean identity. The other thing you'll need is the relationship between the tangent and the sine and the cosine. So you have the tangent of theta is the sine of theta over the cosine of theta. Now, we didn't cover it too much. We just made mention of it, so I'll put them in blue over here, because there are some other, if you will, related identities, such as the secant of theta, which is 1 over the cosine of theta, and the cosecant of theta, which is 1 over the sine of theta. So secant and cosecant, you should have some general sense when you get to calculus what they are. And I remember them because the C's and the S's go together. So it's always the opposite. If it's a C there, it's a sine there. If it's an S there, it's a cosine there. That's the way I just remember. It's the opposite. Okay, but we need those basic trig identities. And you can also put the cotangent in there, which is just the cosine over the sine. But we won't worry about that too much. But you should be familiar with that a little bit. And then we started introducing some other, and we proved yesterday that the sine of 2 theta is 2 times the sine of theta times the cosine of theta, or cosine of theta times the sine of theta. It doesn't matter what order you write that in. And in addition, we had one for the cosine. There's actually 2 variations for the cosine, and 1 minus the sine squared of theta, or the, or cosine squared minus sine squared, excuse me, or cosine squared minus sine squared. There's 3 different versions of this that you'll often see. That's one version. The other version, if you use Pythagorean identity and replace the cosine squared with 1 minus the sine squared, you're going to get 1 minus sine squared minus another sine squared gives me minus 2 sine squared theta. Or I could replace the sine squared with 1 minus a cosine squared and minus a minus, so I'm going to get my 2 cosine squared theta minus 1. So these are the double angles for the cosine. 2 cosine squared theta minus 1. So we have 3 different variations. Of these, it doesn't matter which you use, but the more important one is the sine of 2 theta. This is the one that you'll see frequently used. And what we didn't do, and I'm going to list them here, you can have sum and difference angles. So these, we're not going to derive these. I'm going to show you in a minute. They're derived in the textbook. And you can do it simply by using the identities, and I'll put those on the side for the sine and cosine in terms of the natural exponential function. But for example, you have the sine of, say, a plus or minus b is the sine of a cosine of b plus or minus, depending upon what there, and I have my sine of b cosine of a. That's addition and subtraction inside the argument of the sine, and a similar one for the cosine. So you have cosine of a plus or minus b is the cosine a cosine b. This has an opposite sign, so it's minus plus. So this opposite sign here, where there it's the same sign. And then you have the sine of a, sine of b. Okay. I move these out of the way, but those are going to be the important ones. As you see, there's a lot of identities here, so it's kind of hard to memorize them all, but if you use them enough, you will start to memorize them. Let's put some more over here. These were the sum and difference. We also have those with double angles. I'm going to show this one today. We have something for the half angles if you want to look at those as well. I'll kind of show one of them today. We have like the sine of theta over 2. Well, you can show that that is equal to, or let's do it I'll put it as a sine squared for now. And we just take the square root to get it for the sine. Sometimes you see it as a sine squared or the other one. And this is equal to 1 minus the cosine theta over 2. And we have a similar one for the cosine squared. And this is called the half angle identity. 1 plus cosine theta over 2. Now if I want cosine theta over 2, I just take the square root, plus or minus the square root, depending upon what sign that you might need when you do that. So these are essentially our trig identities, and I'm including with these the idea that we have this, the Euler identities, and we have e to the I theta, cosine theta plus I sine theta. And you have the two for the sine and the cosine. So you have the sine, excuse me, sine of theta is e to the I theta minus e to the minus I theta over 2I. It'll be an important one, especially if you're doing science and engineering. And cosine of theta, you can show just by using this relationship and adding and subtracting, you get e to the I theta plus e to the minus I theta over 2. That's 2I, that's 2. Okay. So these are trig identities. And what do we want to be able to do? So there are two different types of problems we want to attack with all these identities. So there's two types of problems. That you'll come across in calculus and other high-level math courses. One is to just evaluate these for the given argument. So one thing you want to do is just learn how to evaluate given the argument of the function set. And I'll show you what I mean by that. The second thing we want to be able to do, we want to use these to simplify trigonometric expressions. So another alternative is to use to simplify a more complicated trig expression. Complicated trig expression. Because a lot of times you're solving equations and you kind of manipulate the equation. You want to get into a nice workable form, and you start out with something that looks complicated. By using these identities, you can then put it into a different form. So we're going to practice manipulating trig expressions into different types of expressions. equivalent expression. So it's rewriting from one trig expression to another, as opposed to a strict evaluation. Okay, so let me go onto the textbook and show you how you can actually derive those formulas. Yesterday we derived formula 3 using the Euler relations here. Let's show you where that is located. So here's an example. If I would put in my sign of a plus b, and I use the Euler relationship, e to the I of the argument, a plus b minus e to the minus I times the argument, a plus b over 2i. Then you go through a series of algebraic manipulations. You add 0 in. This is the same expression. You know, one is plus and one is minus. So I'm adding 0 in because this cancels with that and the other cancels with that. What happens then, you know, you manipulate everything, and it takes a lot of algebra to do this. And eventually you can get it down to a sine term with the a cosine term with the b, and then another sine term with the plus over here, and another cosine term. So you get the sum angle identity. And you can also do the same thing to look at the sum angle for the cosine, as well as the minus 1 as well. So you can do both of those, and it's just the algebra. So you get these, as I put up there, sine of minus, you can do the same sort of thing as well. It's just algebra. Whereas in a more traditional pre-calculus textbook, there's a lot of geometric arguments that you make to come up with these. Here we can avoid all those complicated geometric arguments and just do it all with algebra by using what Euler provided with us. Let's take I said I would kind of take a look at that cosine squared. This is a little easy to look at. So this is the half angle identity. So for cosine squared, I'm going to put in my my Euler definition for the cosine. It's e to the I, and the argument was theta over 2, plus e to the minus I, the argument over 2 squared, because there's a cosine in the parentheses, and I'm squaring it. So I simply square the top and the bottom, FOIL this out, I get this, rearrange it a little bit, we're just doing algebra. You should go over these. Do you understand the algebra that is required? Because this is kind of critical. Then when I get to this stage over here where I have a 4 down there, I factor out a 1/2. So that changes that 4 to a 2. And then this over here, if I look at that, I divide the 2 into each, so that's 1. And this, what remains over here is just a cosine of theta. So that's all it is with the 1/2. So there's my half angle identity that I have as well, that I just derived for cosine squared. And if I want, I could take the square root and I would have these two variations on that. Okay, so let's see the types of problems that we're going to consider. Now that's kind of enough with that for now. So you should, be familiar with these. You might want to write them all down on a piece of paper and have them accessible, so on a test you'll be able to quickly reference them as needed. So I'm not going to have you memorize all of these. Some of them you will, remember because you'll use them a lot, and that's fine. But let's take a look at the two different types of problems now you'll be asked to solve. So here's an example of a problem that's typical of the first type that you might be asked to solve. You're given the following, and you want to simplify the given trig expression using the identities. So for example, say you have the cosine of theta plus pi. Okay, here I have a sum in the cosine. So what am I going to do? I'm going to use the sum identity for that. So what is that? So this is Now using the sum identity, remember it's the cosine of A, which is theta, times the cosine of B, which is pi. This is plus, but the cosine is minus. So you got to take care of the sign there. Minus, except that minus, I put plus. And then I have the sine of that angle and the sine of that. So it's the sine of theta and the sine of pi. Okay, I can compute the sine and cosine of pi. Cosine of pi, remember, is minus 1. So this is equal to cosine of theta times minus 1 minus sine of theta, but the sine of pi is 0. Okay, the cosine is negative 1, but the sine is 0. So this just gives me minus the cosine of theta. So this simplifies to that. Very simple. Plug it in and see what you get. Okay, why don't you try this one for me? Let's do this other one. So you can try one and see how well you can do. So say I have the sine of theta minus pi over 2. So use the difference angle to find that and simplify it. So plug it in and see what you get. I'm doing it in my head and see how it comes out. I think this is it, as I'm doing it in my head. 2 different ways. Does anyone want to see how I got that, if I did it correctly in my head? Okay, so let's apply the property right now that we know for that. You can look it up there. I got it in my head. So this is equal to the sine of theta cosine pi over 2. That's minus, so this is minus. So it's the sine of pi over 2 cosine of theta. Okay, now we plug in, because that's what, just by using that trig identity for the cosine. Cosine of 90 degrees is 0. The sine of 90 degrees is 1. So this gives me sine times 0, so that's gone. So the only thing that remains is this minus 1 times the cosine, so it's just the cosine of theta. All it is. Now it's interesting because this is also shows you, if you were looking at this graphically, so there's always another way of looking at these problems. If I did this over here, here's my trig function here. Let me start with my cosine over here. So there's pi minus 1. I come over here. So there's my cosine of theta. And let's put the sine over here as well. Well, remember when we do this, this shifts the argument. If I look at sine of theta minus, we're going to see this later on in the textbook when we start manipulating graphs of these functions. Well, when I subtract, I move, in this case, 90 degrees in this direction. So what happens over here? This would be given as follows. This is my sine would continue to go here. And it would shift this 90 degrees, so it would look like this. And that would be sine of theta minus pi over 2. We'll put it in color. You don't need to know this right now, but I'm just kind of showing you what's to come. But notice the black and the red. Well, they're very similar. They're just the negative of each other. Because if I take the negative of the black I get the red. With the negative of the red, I get the black. So you can see the connection graphically as well as algebraically. This was all done algebraically. We're going to see later on when we start analyzing trig functions more in their graphs, this will come up. But it's also reflected by these trig identities. So you have a visual versus an algebraic way of looking at these things. And they'll both be very important. Okay, let me give you another one to try. So try this one. Say the cosine of, let's see, put this as, let's see, I don't want to do this. Let's see, cosine, what do I want to do? Let me make it a simpler one. Don't make it too complicated. Yeah, okay, do that. Do this over here. The combination of things happening here. So theta plus pi over 2. See if you can, now you got to use two trig identities, a half angle identity as well as, if you will, full angle identity. That's a little more complicated. So see if you can simplify that and just write it with an argument cosine of theta. So try that and see what you get in the end, and we'll see what happens. So this is a half angle, so what I could do is write it as this. Take this, it's half of cosine squared, I just take it and I put my argument over here, so it's 1 plus cosine of the top of the argument. So I'd end up with my theta plus pi. Okay, and here's my over 2. I'm not done yet. So everyone see that because I had my cosine squared is equal to 1 plus cosine of the argument. Cosine squared of, we have this. I'll write it up here just so you can see the pattern. Cosine squared of, say, I'll call it a over 2 because I'm using theta over there, is just equal to 1 minus the cosine of just a, and the 2 comes down here. 1 minus, right? Or 1, yeah, 1 plus. The sine squared is the minus, cosine squared is the plus. Then what I need to do, I need to replace that. So see if you can take it from there and continue on with that. And see if you can simplify that as best you can. That's it. Now how to just in the argument of the cosine. I use the sum angle, and it's always minus, but then cosine of pi is -1, sine of pi is 0, as you can see over here. Cosine pi is -1, the sine of pi is 0. Okay, so that's the first type of problem, just manipulating those expressions, if you will. Just plugging them in and simplifying them. Yes, Ashley, have a question?
Yes, I'm having trouble figuring out which identity to use when I see a problem that sometime in this class, even if you want to
Anytime you see a 2 down here, you're going to use the half angle identity, because this is the argument, it's the half angle. So if there's a 2 in the denominator, you're going to use the half angle identity. If the 2 is in the numerator, such as the sine of 2 theta, then you're going to use the double angle identity. So you're looking for 2. If it's up here, you're going to use this. If it's down here, then you're going to use, if it's cosine squared, then you just get rid of the square root, and then just work it from there. Anytime you have a sum or difference over here, if you're adding or subtracting in the argument, then you're going to use the sum or difference identities. So in this case, since I'm dividing by 2, I'm thinking this is some A. That's my argument A. I have some angle A divided by 2. So I'm writing that as my cosine of A, just using that trig identity. And then I replace A with what it's equal to, theta plus pi, and that gives me this sum of the angle, which turns out to be the difference of these cosines and sines, respectively. It's where the 2 is, that's a big thing, and whether I'm adding or subtracting over here. Now, if I put a minus pi over 2 over here, you're going to see it's not going to matter. We'll put minus pi over here. Well, this will change this to a plus, but everything else will remain the same. So it's going to give me the same answer, whether I have a plus or a minus there. You can kind of see that by plugging and substituting in it. So that sort of thing. Let me give you one more to try and see how this works out. See if you can figure this one out. And we'll come back to that graphing at the end of the course. I like to do that at the end because that's when you most need it. And the calculus is early on, so you should have a good sense for that. I like to treat it twice as we go along here. Here's another one to try. Say I have the sine of 4 theta. See if you can figure out that. I mentioned about 2, but I didn't mention about 4. Now, some people may have difficulty getting started. If you have difficulty getting started, this is the way of thinking about it. Think of it this way. Hopefully then something will spark in your mind and then you'll see what to do. It's kind of bootstrapping off of that same double angle identity twice. So this is the identity you're going to be looking at. I'm going to put A instead of theta just so you can kind of see. You're going to use the sine, and you're also going to use this one. You can use either one. I'll put the let's just use this one. We'll use that version of the cosine of that 2 angle. Okay, so what would I write? Well, I see this as this. So I can write that as, this is my A now. So it's 2 times the sine of 2 theta times the cosine of 2 theta. Because that's my argument A. But I still have the sine of 2 theta. Well, I can continue to apply that double angle rule over here. This is equal to 2 times the sine of, I have a 2, the sine of 2 theta, write that in this way. That is now equal to, so this right here is now equal to 2 times the sine of theta cosine of theta. Times, let's take a look at this part now. That's the cosine of 2 theta, which is equal to this. So it's a cosine squared theta minus sine squared theta. Well, I can put the 4, 2 times 2, I'll put the 4 out front, and I can just leave it like this. You could try and manipulate this and show it's equivalent to something else, or you can just leave it like this. Sine theta cosine theta times cosine squared theta minus sine squared theta. Now, I wouldn't do any of the simplifications. I would just write it in that fashion. And that's it. I wrote it all in terms of the sines and cosines, just having theta as an argument. Okay, so we'll give you some basic ones of these to try, just applying the trig identities as given, and from that, evaluating and getting a different trig expression. Now, ideally, what you might have, and this is hard to recognize, you could have this expression in something you're solving, and it'd be great if you could then recognize you could write it simply like this. Going from here to here is hard, but here to here, to recognize that, probably next to impossible, unless you are really, really, really aware and you can kind of see those patterns coming out. Yes, Ashley, have any questions?
What did you see in that problem that made you to continue on?
I have a cosine 2 theta. I want to, in the end, I want to have all, the objective here is to have just sine of thetas and cosine of theta. Not divided by 2, not multiplied by 2. I just want to have a theta in the argument. In the end, that's what I have, theta, 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 and theta. I want to keep going until the argument is just an argument of theta. Here I started with a 4 theta, and then I ended up with an argument in 2 theta, and then I got rid of the 2 theta to just get thetas in both of them. So this one gave me that, and this one simplifies to that. I use both of these identities. My argument, I just want to have theta in the argument. That's the objective here. Well, I don't want to have anything other than a 1 multiplying my variable in that argument there. Okay, so those are these types of problems for using trig identities. We just want to make sure you know how to evaluate them by plugging things in and then simplifying. Okay, so that's the first type. Then the second type is to use those trig identities to verify, or sometimes we say prove, if two expressions are equivalent to each other. So the type 2 problems they deal with how do we establish the equivalence of two trig expressions. And sometimes people call it proving that this trig expression is equal to another trig expression. So let's take a look at an example. So for example, this is what I might have. You're not solving an equation here. So when typically we should use a different notation other than the equal sign, but let me just kind of write it and I'll talk to that in a second. So we have a problem that might look like this. Now I'm going to use x instead of theta. Doesn't matter what I use. I have the sine of x over cosine of x plus 1. And I have another expression, 1 minus cosine of x over the sine of x. Now, what I want to show is that these two are I want to determine, are these two equivalent to each other? Now, we use the equal sign. Typically, however, we really should be using this. Because in this case, we are not solving this equation for x. This is not an equation. This is just an equivalence. For example, let me put it in a simple way. Say, for example, I had 2x or 2x plus 3x plus 4 minus 2. And I would say that is equivalent to, although we write equals, we really should be using 3 lines, it's equivalent to 5x minus 2. That's all it is. So I would say, can you show that this is equivalent to that? That's why the equal signs are used here. We're not solving this as an equation for x. I really would prefer if we use the right notation, but this is, you have to understand it in the context in which it's being asked. So it's like a language where you use the same phrase or the same phraseology or word in different contexts. It has different meanings. So in this case, when I use the equal sign here, it's used more as a noun. This is its noun usage, meaning this and that are just two equal representations with a different name. Here's this name, here's that name. As opposed to what we're going to be doing next time, we're going to be solving trig equations. For example, you might look at cosine of x, minus 1/2 is equal to 0. That's a trig equation that we're going to solve. In this is used as a verb. We have to perform an action. We have to find the values of x that make it a true statement. Here, it's not the same thing. And I know this causes a lot of confusion with students, because as soon as they see this, they think they're trying to find the x, but that's not what we're trying to do. So let's see what we're actually trying to do here. That's the hard part about mathematics. We use the same symbol to represent two conceptually totally different things. And if you did that in English, the same word can be a noun and a verb, it will cause confusion unless you point it out. And that's what's not done enough. We don't point it out enough. So we're actually doing, and we have a notation for it, and that would be 3 lines and show their equivalent. Okay. When you're given that, you have 3 possibilities. So this is my type of problem that I'm given, type 2. Sometimes in some books they'll say, prove that they are equal. And people call it a proof when you're doing that. Or show that they are equal. Sometimes they'll say that. Okay, so given this, you might have, I'll write it here. You have expression 1, and then we'll solve that one. Is equal to or equivalent to, and we're trying to establish, is it equivalent to expression 2? So trig expression 1, is it equivalent to trig expression 2? We have 3 approaches that you can take. One is you can start with expression 1 and try and using trig identities manipulate it so it looks exactly like expression 2. So you start on the left. So one is you use trig identities to show that expression 1 can be written as expression 2. Okay, the other approach, instead of on the left-hand side, you can do the same thing for expression 2. So we're going to use trig identities to show that expression 2 can be written as expression 1. This is expression 1 as 2. This is expression 2 as 1. Expression 2 can be written as expression 1. Then the third approach that you can take is work with both expressions to show and simplify so you get the same exact thing on both sides of the equal sign. So work with both expressions and show they are equal. So let me take that and do it 3 different ways so you get a sense for how that works. Now, usually there's one technique that's a little bit easier than the others. One of those approaches or techniques tends to be a little bit easier than the other ones over here. So let's start with this approach 3 for that one. So I have the following with the cosine, the sine over the cosine, the sine of x over the cosine of x plus 1. And I want to show that it's equal to or equivalent to 1 minus the cosine of x over the, if you will, sine of x. This is my example. So now this is going to be an example. I'm going to use this approach on this problem. I'm just going to do the one. The other way, you can do it, but it's a lot more complicated. So how might I use it working with 2? So what I could do is just simply cross multiply. So to show that they are equal, I would cross multiply. So what do I have? I have sine times the sine gives me sine squared x is equal to 1 minus the cosine of x times 1 plus the cosine of x. I just change the order. Okay, so doing that, multiply this out, so I'm going to get 1. I'm going to have minus cosine plus cosine cancel out, but I'm going to have minus the cosine squared x, right? If I distribute that out, I will get this. The middle term will cancel out, because it's plus and minus. Well, then what I might do is I might add cosine squared to both sides. So on both sides, I'll turn around and I'll just add cosine squared x. So what do I have? On the left-hand side, this is just sine squared x plus cosine squared x equal to 1. But what is the sine squared plus the cosine squared? There's my other trig identity. That's just 1. So I get 1 equal to 1. I've shown that these two different looking expressions give me the same exact result in the end. So I could either have that or that. Plug in any value of x, I will get the same exact value out every time. It's kind of like, 5x, plus 2 is equal to 2x plus 3x plus 4 minus 2. Get the same thing. So, and I use this approach. Let's take a look at some of the other approaches with some other ones where we can actually manipulate it differently. Let's see. I got another one over here. I'm trying to make them up as I go along here. Okay. So we have this. That's done now. Now, these can be challenging. It does take some time to learn how to manipulate these things, and you have to be looking for when you can apply your trig identity. And that's why it can be difficult. So let me see if I have another one handy over here. I was kind of busy with my morning class. Let's try this one. So I have this one. I have sine of x minus the cosine of x quantity squared. And I want to show, is it equivalent to 1 minus sine of 2x? Okay, so what could I do? Well, let's just work with the right-hand side. Let's see if I can in some way rewrite this in some way to make it look similar over here. I'm going to just work with one side of that equation, if you will. That's what I'm doing here. Or in fact, let's just work with this side. I'm going to work with the left-hand side. So I'm going to leave that the same. I'm not going to change everything. Let's just manipulate this. So let's rewrite this in the following way. I'm going to do this as the sine of x minus the cosine of x times the, I'm just working with the left-hand side, sine of x minus the cosine of x. And what do? I just distribute this. So I'm going to get a sine squared x, right, minus sine x cosine x. Okay, then I'm getting another minus sine x cosine x. I'll just switch the order there. Plus cosine squared x, right? Okay, so let's rewrite. I'm not doing anything at all with the right-hand side. So I'm everything in the left-hand side, trying to transform it into that. So what do I have over here? Let's put these two together. I have sine squared x, cosine squared x, like that, and that, minus 2 times the sine of x times the cosine of x. Well, what is sine squared plus cosine squared? That's my Pythagorean idea. That's just 1. That's 1 minus 2 times the sine of x times the cosine of x. But what is 2 times the cosine? Well, that's my double angle identity. So this is 1 minus, this is just the sine of 2x. Exactly what. So I've shown that this expression is equivalent to that expression, so I'm done. So that's how you just transform one side into the other. I could have done it the other way, but let me show you how you might do it that other way. It's a little bit harder to do if you want to do the right-hand side. So now I'll work just with the right-hand side. Kind of doing this backwards, and it's harder to do. Well, you can do it, but it's much harder to do. So now I start with 1 minus the sine of 2x, but I'm going to replace that with 2 times the sine of x times the cosine of x. Now this would be very hard for people to see.
Lost you.
I'll set it up again. There, that's Blackboard again. What is my throughput rate? Let's see. Only not that much. 91 kilobytes per second, 98. So I'm borderline. it might get choppy. They're throttling back. They do that all the time. Now this is hard because I'm here to here. Then I'd have to recognize that, okay, that 1, I'd replace it with sine squared plus cosine squared. That's why this is hard to go from this to that. So it is usually dependent. This I'd have to recognize that I could write 1 as sine squared x. I don't expect anyone to do this, but this is how it would be if you could do it that way. Minus 2 sine x cosine x. And then I have to recognize that this is nothing more than sine x minus cosine x times sine x minus cosine x. That's another tricky thing to recognize, but you might see it because put that at the end and it's kind of built out there. And then I rewrite that as sine x minus cosine x quantity squared, and I got the other side. So those are the 3 approaches. Now, the most common one is you work with everything together, unless you can see in a few steps how to transform this. But the first step here, I would get rid of, since there's no squared, I get rid of the parentheses and start working with it. And again, we're not solving anything for x, we're just verifying that these 2 are equivalent expressions. Next time, we'll be solving equations, and we will be solving for x, unlike what we're doing here. This is just establishing that this trig expression is equivalent to this. So, for example, if I had this in expression, I could replace it with 1 minus sine of 2x, and then maybe solve an equation that way. The purpose is to rewrite that so you can actually simplify something a little more easily. Okay, let's try another one. These tend to be challenging and or difficult. So you have to practice a lot of them, and then you start getting better at it. Because it's looking for the patterns, and it's sometimes hard to see the patterns right away. And the only way to see patterns is to kind of work lots and lots of problems. So this is always problematic for a lot of students. So let's try another one. So let's take 1, and I'll let you try this. Over the tangent of x minus the tangent of x, and I want to show that that is equivalent to 2 over the tangent of 2x. This can be a challenging one. See if you can validate that. Try it for a few minutes, and then I will take over. Now, as a hint, anytime you see the tangent, the hint is to replace the tangent as the sine over the cosine. Tangent of some argument is the sine over the cosine. Use that, and then start to work it. It's easiest to take the tangent and change it. Unless you have something called secant in there, secant squared. You'll learn a little bit about that when you get to the calculus. But that's how I would approach this to start with. And I could either work with everything, or for this one, I could do both types of problems there. In fact, I'll do all 3, show you all 3 techniques to validate that that is a true expression. But see if you can pick one yourself and validate that. Now, I will look at what you do. So a lot of students, they get part way and then they just write the answer equals and they say, yes, it's equal. Now, I'll look for the steps and make sure that there's logic. Many people try and snow professors by just manipulating here and then just suddenly make it miraculously equal to the other side and say, oh, they're equal. I should trip it up by putting some that are not equal in there, but usually I don't. But I look for all your steps. So you have to show steps on here. Here the steps are very important. It's kind of like a proof. It's a simplified show proof. Now there is actually a fourth technique where you can work and manipulate both to show that they're equivalent. That's kind of like the third one. Kind of like the third approach. Okay, so let me start by transforming this into that. This is a reciprocal, right? I'm going to put these over a common denominator. And that common denominator is going to be the sine x cosine x. And what do I have to put over here? Well, here I have to put another sine of x. And here I have to put a cosine of x. No, excuse me. It's cosine and sine. Keep me awake. Sine, yeah, because that's where I get my identity. Cosine. So I have the same denominator now. So this now gives me cosine squared x minus sine squared x, right? But what is cosine squared minus sine squared? Well, in that case, we'll recognize we have this. We have cosine of 2 theta is cosine squared theta minus sine squared theta. Okay, so this is nothing more here than cosine of 2 theta. Two x, not theta, 2x. I'm still staying on the left-hand side over here. I also have a relationship that says the sine of 2 theta is 2 times the sine of theta times the cosine of theta. So what can I do? Well, I could actually put a factor of 2 here, but I have to divide it out by putting it there. Okay. Now this becomes, let me put it right over here. I haven't done anything with the right-hand side. Everything's with the left-hand side. So over here I have 2 times my cosine of 2x over this 2 sine x cosine x just gives me sine of 2x. Okay, I'm still not done. I can rewrite this now as 2 over, and I can take the reciprocal. So there's the sine of 2x. So you have to be through algebra. Cosine of 2x. Well, that's the sine over the cosine. What is that? That's the tangent. So it's 2 over the tangent, but now the argument is not x, but the argument is 2x. Ah, I've shown I got the same thing over here. So this is the skill that you need to kind of work at and manipulate. And that's how you use the various trig identities. So you see these trig identities come into play over here. And of course we used on the other problem, sine squared plus cosine squared is 1. Here we use the tangent. So all the various trig identities we were using to manipulate that. Now I could, on the other hand, go the opposite direction. I could start with the right-hand side. So let me take a look at that. So here's an alternative way of doing it. And then I'll do both together. So that establishes that this expression is equivalent to that expression. So let's see. Instead, I'm going to now start with the right-hand side and manipulate that until I get the left-hand side. Okay, so what I'm going to do, I'm going to write the tangent using the sine over the cosine. Well, since that's the reciprocal, that is nothing more than 2 times the cosine 2x over the sine of 2x, right? Now I'm going to use those trig identities over here. So cosine of 2x, remember, is cosine squared x minus sine squared x. That's cosine of 2x. Sine of 2x, well, that's equal to, in this case, 2 times the sine of x, right, times the cosine of x, right? What happens? Well, right away, the 2's cancel out, so I don't have to worry about them. They are gone. Let's write this one at a time, so I can rewrite that as my, if I wanted to, cosine squared x over the sine x cosine x minus sine squared x over the sine x cosine x. What can I do? Well, I can see I can cancel one of the cosines right here. That gives me cosine x over the sine of x. I can cancel one of the sines terms over here. That gives me sine of x over the cosine of x. Then I can recognize this. I can rewrite that as 1 over the sine x over the cosine x minus sine x over cosine x. But what is sine x over cosine x? That's the definition of the tangent. This is 1 over the tangent of x minus the tangent of x. So I started with this, and I ended up with the left-hand side. That's another way of showing it. You're not solving anything, you're just kind of showing that they are equivalent, or proving that they're equivalent. First case, I started with the left, got the right, and I started with the right, and turned into the left. Then let's take a look at the third approach. The third approach says, let's use both and make sure in the end I get the left and the right equal. This is usually the more common approach for students, but the other approaches are very good because it gets you thinking in different ways, and it's kind of very beneficial. So now I'm going to use both sides. First step is to change this into the sine and cosine. Well, that's the reciprocal, so I'll skip a step. I'll make this cosine of x over the sine of x minus sine of x over the cosine of x. I did 2 steps in one over here. Okay, in this, let me flip this as well. So that's 2, and this becomes the cosine comes on top, because if I put that on top, so I have it's sine over cosine, but when I take it reciprocal, it's cosine of 2x over the sine of 2x. Then what would I do? Well, I'd get rid of these sines and cosines of double angles and rewrite them as cosine and sines of single angles. Use a trig identity, so that's equal to my cosine squared x minus my sine squared x, okay, all over, 2 times cosine of x times the sine of x, right? Now I can cancel out those 2's. Now let's get rid of everything in the denominator. How could I do that? All I need to do is multiply both sides by, or cross multiply, if you will, cosine x sine. This will cancel with that. And then if I distribute this over here, what do I have? I get cosine, I'm going to distribute that to both terms, cosine squared x, I'll put it over here, sine x over sine x. And you can see that sine's going to cancel. And then I'm going to have sine squared x, and then I have cosine x over cosine x. Cancel out these things over here, and lo and behold, I have the same thing that I have on the both sides. So I work with both sides, and I've now shown that the left, it's equal to cosine squared x minus sine squared x, which is equivalent to the other side, which is also cosine squared x minus sine squared x. So I validated that identity, if you will. That's another trig identity we could have. But I used both sides. I worked on both sides. I didn't do exclusively one to the other. I worked on both simultaneously.